In this video, we'll talk about how we can evaluate one of our exponential indeterminate forms, like 1 to the infinity, 0 to the 0, or infinity to the 0 with L'Hopital's rule. So the example I want to look at is the limit as x goes to infinity of the quantity 1 plus 1 over x to the x power. Okay, so first, let's just see what happens when we plug in. So if I plug in infinity, in the parentheses, this just becomes 1 plus 0, which is 1. And the exponent is going to be infinity. So I have something of the form 1 to the infinity power, which is one of our indeterminate forms. And remember, this technically means our exponent is going to be a huge number. So our exponent is a huge number. The inside of this parentheses is getting really close to 1. It's technically a little bit bigger than 1 because you're doing 1 plus a really small positive number. So inside the parentheses, we have something that's a little bigger than 1. Okay, and this is one of our indeterminate forms. It's not something I can do L'Hopital's rule on now because it's not 0 over 0. It's not infinity over infinity. So I'm going to have to simplify this somehow to get it into a form where I can do L'Hopital's rule. So here's how we'll do that. I'm going to begin by letting my limit be y. I'm going to let y be the limit as x goes to infinity of 1 plus 1 over x to the x power. And then I'm going to take ln of both sides. Take ln of both sides. And the reason for that is there's a log property that says that if I have a power like this x power inside of a log, I'm going to get to move that in front. So it'll get rid of this exponent here. Or at least it'll move it. All right, so let's do this. Let's take ln of both sides. Ln of y equals ln of that whole limit. The limit as x goes to infinity of 1 plus 1 over x to the x power. Okay, so let's work with the right-hand side. I have ln of y equals this whole thing. So I can move this limit in front of the ln. So I get ln of 1 plus 1 over x to the x power. That whole thing is inside of this ln. Okay, so I have the limit in front. In fact, maybe I don't even need this parentheses. And I can do this since the ln function, ln of x, is continuous. Because that's continuous, we can pass the limit outside. That was one of our theorems about continuous functions, and when we had limits, if I have a continuous function, I can move a limit either inside or outside of it like this. Okay, now the ln is right next to this thing with a power, so now I can use my log properties. So the limit as x goes to infinity. Now I can bring the x in front of the ln. So x times ln of 1 plus 1 over x. I couldn't do that at the first step, because in the first step, this 1 plus 1 over x to the x power, it wasn't right inside of this ln. This other limit was in front of it, and I had to deal with that first. Okay, but once we got it to the second step, then that thing to a power, that was right inside of this ln, and now I can move that power to the front. So let's try plugging in one more time. If I plug into this x, I'll get infinity, and then I'll get times ln of, the inside of the ln is getting close to 1, so we have something of the form infinity times 0, which is another indeterminate form, but we saw how to handle these infinity times 0 indeterminate forms in the previous video. Remember, the idea was to rewrite these as a fraction, and to do that, we'll bring one of these terms, either the x or the whole ln of 1 plus 1 over x to the denominator and reciprocal it when we do. So with the limit as x goes to infinity, and I think it's going to be a little bit easier to just move the x to the denominator, because I'll reciprocal it and I get 1 over x. So I'll keep the ln of 1 plus 1 over x on the top. And now let's check what happens when we plug in. So when I plug in on the top, I'll get ln of 1, which is 0. And on the bottom, I'll get 1 over infinity, which is 0. So I have 0 over 0. Now we have something we can use L'Hopital's on. All right, and now let's do it. So this equals, I'm going to write LH, because we're using L'Hopital's rule on this step, equals the limit as x approaches infinity. I got to do the derivative of the top over the derivative of the bottom. So for the top, I have ln of some stuff. This is going to involve chain rule. Chain rule will say, okay, do 1 over that stuff inside the log, 1 over 1 plus 1 over x times the derivative of the stuff inside the log. Derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. And on the bottom, the derivative of that 1 over x is negative 1 over x squared. So I get this perfect cancellation. These two terms cancel out perfectly. And now if I plug in, I get 1 over 1 plus 1 over infinity is going to 0. So 1 over 1 is 1. Okay, so does that mean my answer is 1? Well, I got to think back to where did this whole chain of equal signs begin? This whole thing was equal to ln of y, not y. So that tells me I can now say thus. I now know ln of y is equal to 1. But remember what y was. We started off by saying, let's just call our limit that we're trying to find y. So I just need to find y. I know ln of y. Ln of y is 1. And if I transform this to exponential form, we'll get y equals e to the 1. Because the base of ln is e. It's log base e. So e to the 1 is just e. And that's what this limit equals. It's kind of bizarre that this limit right here, there's no trace of e in it right now when we look at it. This is a 1 to the infinity type form. It ended up equaling e. Okay. So it turns out that there are a bunch of equivalent ways to define what e is. And a very common definition of e is to start off by defining e as the value of this limit. The limit as x goes to infinity of 1 plus 1 over x to the x power. To define that as being e. So in our case, in our course, we had given an alternative definition of e, which is equivalent to this, it turns out. And our definition of e let us do things like take the derivative of ln of x. And because we already knew how to take the derivative of ln of x, that's what let us get to this step where we could do the derivative of the top and the bottom and use L'Hopital's rule to eventually get that this limit was e. Alrighty, so I want to end this video with just a recap of the different types of indeterminate forms and how we can handle them with L'Hopital's rule. So with 0 over 0, or a plus or minus infinity over a plus or minus infinity, our strategy is just going to be to try L'Hopital's rule, try LH. Even in that second form, we can try L'Hopital's rule. I don't have to all the time if I want to use our previous methods from chapter 2 to simplify or do things like use the highest power of x on the top and the bottom because I have an infinite limit of a rational function. I can do stuff like that, but if I want to use L'Hopital's rule on these, I can. For 0 times infinity, we had seen our strategy was to bring one term to the denominator and reciprocal it. And then often we'll have something of the form 0 over 0 or infinity over infinity. So then we can try L'Hopital's. We've also seen an example of an infinity minus infinity thing. And with those, I also have to sort of simplify it first a little bit. So that could happen either with a common denominator. We could try a common denominator. Another strategy that we've seen in the past for subtractions is sometimes it involves a conjugate. So we'll have to do some sort of simplification to be able to get it into a fraction form. And maybe once it's in a fraction form, then maybe I'll be able to use L'Hopital's. So if you do this and then, let's put this small then LH if possible. Okay, and then the final type of indeterminate form that we now have is these exponent ones, 1 to the infinity, 0 to the 0, or infinity to the 0. And our strategy here was we set y to be equal to the limit, or some new variable. And then we take the ln of both sides. And as we saw above, hopefully we'll be able to simplify that to a fractional form that we can then do L'Hopital's rule on. All right, in terms of our goals, we finished our last goal for this section, which is over the last few videos, we've talked about how we can transform other types of indeterminate forms into forms that we can actually apply L'Hopital's rule on.